resonance to frequency response to resonance. So resonance may be loosely described as the condition existing in any physical system when a fixed amplitude sinusoidal forcing function produces a response of maximum amplitude. So resonance systems can be electrical, mechanical, hydraulic, acoustic, etc. So some everyday examples of resonance. So first is a swing. So when we push the swing, it starts moving forward and backwards. So if a series of regular pushes are given to the swing, its motion can be built. So the person who's pushing the swing has to match the timing of the swing. So if that timing is the resonant frequency, the motion of the swing reaches its maximum amplitude. Next is a singer breaking a wine glass. The singer's voice hits the resonant frequency of the wine glass, a transfer of energy will occur, the maximum transfer of energy. So that's why the wine glass shatters. The next example is a radio. So when we turn the knob of the radio, we are changing the resonant frequency of the receiver. So when the two frequencies match between the transmitter and the receiver, maximum energy transfer occurs. So in a two-terminal electrical network containing at least one inductor and one capacitor, we define resonance as the condition which exists when the input impedance of the network is purely resistive. Thus, a network is in resonance when the voltage and current at the network input terminals are in phase. So at resonance, the input impedance consists only the resistive component. The value of the response will be maximum since the total impedance is minimum. The voltage and current at the input side are in phase, and maximum power occurs at resonance since the power factor is unity. So resonance circuits are useful for constructing filters as their transfer functions can be highly frequency selective. In series resonance, the impedance again is purely resistive. So the LC series combination acts like a short circuit. So this acts like a short circuit. So the entire voltage is only across the resistor. So the voltage Vs and current I are in phase. The magnitude of the transfer function is minimum. Then the inductor voltage and capacitor voltage can be much more than the source voltage. So we will show that later. So for series resonance, we have G is equivalent to R plus JWL plus 1 over JWC. Or we can write this as R plus JWL minus 1 over omega C. So it is said that at resonance, the impedance is purely resistive. So meaning, at resonance, this component is equal to 0. So at resonance, or omega naught L minus 1 over omega naught C is equal to 0. Solving for omega naught or omega naught squared is equivalent to 1 over LC for omega naught is just 1 over square root of LC, where omega naught is our resonant frequency. And the magnitude of C is equivalent to R squared plus WL minus 1 over WC squared. Now, solving for I, we have I just equivalent to Vs over Z. We have Vm angle theta over R plus J quantity WL or omega L minus 1 over omega C. So at resonance frequency, Z is purely resistive, so our I is equal to Vm angle theta over R. So we have Im angle theta, where Im is equal to Vm over R. For the average power, we have this equation, 1 half I squared R. Meaning at power at resonance frequency, we have 1 half Im squared R, or this is in terms of Vm, we have 1 half Vm squared over R. So at certain frequencies, so for example, we have omega 1 and omega 2. Let's say at omega 1 and omega 2, the dissipated power is half. Or we can set our Vm over square root of 2. Or we can divide our Vm, the magnitude of Vm by square root of 2. So the power at omega 1 is equal to power at omega 2 equivalent to Vm over square root of 2 squared over 2R equal to 1/4 Vm squared over R. So omega 1 and omega 2 are called the half power frequencies or cutoff frequencies. So this graph shows the current versus frequency for the series resonance circuit. So we have at resonance frequency, our I is at its peak, or I is at the maximum value. This Vm over R. And the cutoff frequencies or half power frequencies, omega 1 and omega 2, our I is at 0.707 Vm over R. So for the cutoff frequencies, setting Z equals to square root of 2R, we will obtain the values for omega 1 and omega 2 is given by this equation. We have negative, positive R over 2L plus square root of quantity R over 2L squared plus 1 over LC. The bandwidth of a series resonance. Omega 1 and omega 2 are in general not symmetrical around the resonance frequency because the frequency response is not generally symmetrical. However, symmetry of half power frequencies around the resonance frequency is often a reasonable approximation. So although the height of the curve is determined by R, the width depends on the bandwidth. So our bandwidth B is equal to omega 2 minus omega 1. Using the expressions for omega 1 and omega 2 in terms of RL and C, we can get that our bandwidth is just equivalent to R over L. So next is the quality factor. The sharpness of the resonance in a resonance circuit is measured by the quality of Q. Q is not to be confused with reactive power. So at resonance, the reactive energy oscillates between the inductor and the capacitor. So Q is given by 2 pi times the peak energy stored in the circuit over the energy dissipated by the circuit in one period at resonance. Q equal to 2 pi. We have the peak energy stored in the circuit. We can get the maximum energy stored by using the energy stored in an inductor, so 1/2 Li squared, and then energy dissipated by the circuit in one period at resonance. So 1/2 I squared times R times 1 over F naught, or this is equivalent to 2 pi F naught L over R. Looking at this term, 2 pi F naught is just equivalent to omega naught. So our Q just equal to omega naught L over R, or in terms of RC, we have 1 over omega naught RC. The relationship between Q and bandwidth is given by, we have Q equal to omega naught L over R. So this is equivalent to omega naught over the bandwidth. So meaning our Q, thus the ratio of its resonance frequency and bandwidth. The quality factor determines the selectivity of the RLC circuit. So the selectivity of an RLC circuit is the ability of the circuit to respond to a certain frequency and discriminate against all other frequencies. A resonance circuit is designed to operate at or near its resonance frequency. So it is said to be a high Q circuit when its quality factor is equal to or greater than 10. So meaning if you have high Q, you have better selectivity because you can narrow down your uh, frequencies or the bandwidth. So for high Q circuits, the half power frequencies are, for all practical purposes, symmetrical around the resonance frequency and can be approximated as, so we have omega 1 is approximately equal to omega naught minus the bandwidth over 2, and omega 2 is approximately equal to omega naught plus the bandwidth over 2. So earlier it was said that the voltage in the inductor and the capacitor can be greater than the input voltage. The magnitude of V or the magnitude of Vc can be greater than Vm. Take a look at our VL. Magnitude of VL is just equivalent to the Im, the current across the inductor, times the reactance of the inductor. So the reactance of the inductor is omega naught times L. Our Im can be expressed in terms of Vm over R times omega naught L. So if you take a look at this term right here, omega naught L over R is just equivalent to Q. So we have Q Vm. Same for magnitude for Vc. We have Im times reactance 1 over omega c equal to, again we can express Im in terms of Vm for R times 1 over omega naught c. So 1 over omega naught Rc is just equivalent to Q Vm. We notice that the magnitude of VL is just equivalent to Vm multiplied by a factor Q. So VL and Vc can be greater than Vm. So for example, we have this circuit. Find the resonance frequency and half power frequencies. So calculate the quality factor and bandwidth. Determine the amplitude of the current at omega naught or at resonance frequency and at the half power frequencies. Omega naught is just equivalent to 1 over square root of LC. Omega naught is just equivalent to 50 kilorad per second. Or omega 1, omega 2 can be calculated using this formula. Negative positive R over 2L plus square root of R over 2L squared plus 1 over LC. So we have omega 1 equal to 49 farad per second. Our omega 2 is equivalent to 51 farad per second. Our bandwidth is equivalent to omega 2 minus omega 1. We have, or this is just equivalent to R over L equal to 2K rad per second. Our quality factor is equivalent to omega naught over B is equal to 25. Our circuit is a high Q circuit. To a high Q circuit, we can have another solution. So assuming, let's first determine if the circuit is a high Q circuit. So Q is equal to omega naught L over R. So we have solved for omega naught is 25. So 25 is greater than 10. So we have a high Q circuit. So solving for the value of B using omega naught and Q, we have 2K rad per second. Solving for omega 1, we have omega naught minus B over 2. We have 49 K rad per second. Omega 2 is equivalent to omega naught plus B over 2 is equivalent to 51 K rad per second. So lastly, determine the amplitude of the current at omega naught and the half power frequencies. So at resonant frequency for I is equivalent to Vm over R. We have 2 over 10. We have 10 amperes. So at omega 1 and omega 2 for I is just equivalent to Vm over square root of 2 R is equal to 7.071 amperes.